now we are going to do another question where we are looking at energy ideas to be able to solve the problem versus other things in physics we've learned already. So in this problem we have two cats of the same mass. They're going to jump from a 2.5 meter high table. Both are jumping with a speed of 4 meters per second, but they're essentially jumping in kind of opposite directions, so to speak. One's jumping up and away from the table, the other one's jumping downwards. Okay, not straight down though. And what we'd like to do is to calculate the speed of each cat before it hits the ground, like just before that landing point. All right. So I'm going to start off this just like we would with any other question. I'm going to draw a little picture of this diagram to help me out. All right. So we've got our table, and I know that this table is going to be 2.5 meters high. And I'm going to draw a little dotted line here to represent my horizontal. Okay. And we've got one cat, let's see, cat A is jumping upwards. So I'm going to draw a little velocity vector here for cat A. Cat A is jumping upwards at a 45-degree angle. And it'll jump up and then ideally, come back down. Looks a whole lot like a projectile motion problem, right? And then cat B is going to jump downwards at an angle of 45. So there's our B velocity. All right, that one's gonna kind of go something like that. So the goal is to figure out at these landing points what their speeds are. And I'm gonna think about this in terms of energy conservation, because I know as soon as we see a projectile motion problem, our minds don't want to go back to projectile motion in physics, do they? We want to try something a little bit easier, and hopefully this energy thing proves to do that. All right, so let's look at our energy ideas for this problem. So I'll start by just talking about cat B for a second. So cat B is going to start up at this top of the table, and then cat B jumps, and then he's going to start going a little bit faster, right, as the cat approaches the ground. So if I think about this from a sort of work energy perspective, what non-conservative forces are present that would be acting on the cats? Something non-conservative. And hopefully you've kind of thought about this time that there's really not any non-conservative forces. Sure, all of them have their weight acting on them the whole time, but these objects are just, well, not the objects, but these cats are just moving through the air. There's not a whole lot of air resistance here. They're just jumping from a typical table height. So essentially we don't have any of these big external non-conservative forces to affect our overall energy. So that tells us something really important once we've recognized that, and that is the mechanical energy here is going to be conserved. Throughout the entire story. So if we were to compare the overall energy at the beginning of the jumping point to maybe the maximum height up here, or maybe some arbitrary point along the path, we would find that overall amount of energy is going to stay the same. So let's look at what types of energy are present here that we are going to be comparing. So with energy, we've got to compare some places. So ideally, our story tells us what we are supposed to be comparing. So we've got a beginning point here where the two cats jump. We've got that sort of initial spot. And then we've got a later point. It says to find the speed just as they're getting ready to hit the ground. So this ground spot here, and then on the other side, right when these guys they're hitting the ground, we want to try to compare those two places. So let's do we'll do cat A first. We'll go in alphabetical order here. So cat A. So what type of mechanical energy can we say cat A has at this point here? All right, so it looks like they are jumping with a velocity. So the cats actually start with speed versus just like kind of tipping over off the table, then that would mean that they were starting at rest. But these cats actually jump with a speed. So it starts off with a speed of 4 meters per second. So that tells me that the cat definitely has some kinetic energy in the beginning of the story because it's already moving. And then I say, okay, well, does it have the potential to drop further down from where it starts? And we know the cats are jumping off of the table and eventually are going to hit this lower point here. So that's when we say, well, it's probably got some gravitational potential energy too. It's got that potential to fall further down. So we've got some initial gravitational potential energy. So So that's kind of my initial places. There's no springs attached to the cats, so we don't have spring potential energy. And then we look at later points. For cat A, he's going to go up all the way back down. He's going to hit the ground over here. Okay? So at the end of our story, the cats are landing with a speed. Sure, they quickly stop, but that speed just before they land, that's the one that we're looking at figuring out. So it's going to have some kinetic energy at the end of the story. And then also, we've noticed if it starts up at the table and lands on the ground, that's basically the furthest down that the cat can go in this particular story. So essentially what we have here is that at the end, it can't really go down further than that. So we don't really have any more potential energy left over, okay? So now I can try to start using this a little more in detail. So I know that kinetic energy is just going to be 1/2 mvi squared. We know gravitational potential energy is just mgh, whatever that, I'll put hi here for the initial height. And I know kinetic energy is 1/2 mvf squared, okay? And this is where I want to say, okay, well, maybe I can start plugging in numbers and looking for what some certain values are. And I noticed that this mass is present everywhere. So it's in each piece of this algebraic equation. I also know if I really quickly glance at that question again, mass is not given to us. Well, it turns out that that's actually not a problem, which is kind of a common thing, which you've noticed in forces it's happened before, and you're going to notice that that same thing is going to reappear in energy, that the mass can actually cancel out of this equation. So we're left with 1/2 vi squared plus ghi equals 1/2 vf squared. Okay, and we'll do the numbers in a bit. Now let's go to cat B for a second. So we've got 2 cats in the story. We need the velocity of both of them, or speed, I should say. So cat B. All right. So cat B is going to start up here, still same spot, and it also jumps with a speed of 4 meters per second. That's interesting because if I look at this cat A relationship, it also jumped with a speed of 4 meters per second, and it also started at that same 2.5 meter height. Something interesting to note. So it looks like we've got 1/2 mvi squared plus mghi, again, for that initial place for cat B. But then at the end here, when cat B starts to land on the ground, it has also lost all of its height, essentially. So again, it's very, very similar to what we have up here. It'll have some speed just before it hits the ground, and it's lost all of its gravitational potential energy. Masses can still cancel. We get kind of the same algebraic equation. So what we can see here, if this velocity is the same for both of them, this vi, if the height is the same for both of them, then these guys are going to have the exact same speed at the end when this is all said and done. So we didn't need any of those fancy projectile motion equations in order to solve this. We can use a very simple energy conservation portion and get the same answer, only doing one thing. I don't need to solve this twice. I can see right now that those are going to give me the exact same answer. So I'm going to erase this part and let's get this thing solved. Let's figure out what the speed is of both cats. All right, let's start putting some numbers in here and figure out how fast these cats are moving. We've decided already again that cat A is going to be the same as cat B. They are equal to each other. All right, so looking at our numbers here, we've got 1/2 initial velocity, or initial speed, I should say, for kinetic energy, 4 squared plus 9.8 times 2.5 equals 1/2 vf squared. And we can try to figure out what the velocity is from here. So we've got vf equals, 8.06 meters per second if you put all of this into your calculator. All right, so we see the cat speeds up a bit. Now, I would like to call your attention to something here, that in the question, we're asked for the speed of both of the cats, not the velocity. So that's one thing that this energy conservation idea, or even the work energy theorem, will usually give you. Typically, you'll end up with a speed. You might have to do one extra step or so, a couple more things, usually something small if you want to actually report the velocity, which gives us that directional piece to which way these cats are going. So we know that if you have an object projected that way and it's going kind of down into the ground, or this one, he jumps off the table and goes down into the ground, overall, they're both going to be moving kind of at a downward angle of some sort, where this is your horizontal surface and then you'd be angled kind of into the ground, okay? Now, we know that the speed of both of them, we just found that the speed is 8.06. So if I think about this, I know what this, the side of this, or the hypotenuse of this, what could be a vector triangle is, okay? And if you think back to when we were first talking about projectile motion, since gravity consistently just pushes down on your projected object, remember that x velocity stayed the same? So we know that this component here, this x component, this Vx, is going to be the same the whole entire time the cats are moving. And both of them start with this diagonal velocity of 4. One is up at an angle, one is down at an angle, but they both have that same x component when they start. So your Vx for both cats is just 4 cosine 45, and that's taken from the beginning of this story. So they have the same Vx. So at this point, you can report this in component form if you wanted to get the final y velocity. You could use a little bit of trigonometry to get theta. So essentially at this point, you're either using your Pythagorean theorem or you can use trig, and either one of those would eventually report the actual velocity of the cat versus just the speed. And that is energy conservation. On to the next video.